So good evening all. So in this session we will discuss the B tree, that is binary search tree deletion. In the previous class we have discussed about the binary, what is binary search tree, what is binary search tree insertion. Wait a minute. Yeah, binary search tree insertion. So in this class we are going to discuss about deletion. So the three operations are there for the binary tree. So one is search operation, insertion and deletion. So search and insertion already we have discussed. Now we can discuss about deletion operation. In deletion, what is meant by deletion? Just removal of one element from the tree. That is called as deletion. But in binary search tree, we have three type of deletion. So three cases will be there for deletion. So one is first case, we will take deleting a leaf node. Okay, we are going to delete some node. That node should be a leaf node. It doesn't have children. This is the first case. So we are attempting to delete one element or one node. So one node, that node should be a leaf node or no children case. So in that case, this is the first case of deletion. If it happen, so we can delete that node without any problem. So it will not violate the binary search tree property after the deletion. If we are attempting to delete some value, if it after the deletion it will not violate the binary search tree property, means no issues. Otherwise, we have to satisfy the property for deletion also. So here we are attempting to delete the node 78 from the given binary search tree. Check with this example. 78 means first you have to locate the position of 78 where the 78 is available. Okay, so first you can compare with the root node as it is greater. So move with the right hand side child. And then again compare with again when some tree is available. So compare with the 56. And yes, it is greater than the 56. So here 78 is available. Now this delta node will be located. So now we can delete this 78. So because of this deletion, it will not violate the property of binary search tree. So we can delete this value immediately. So no property violation. So this is the first case of deletion. A deleted node should be a leaf node. We can delete the value. So no violation of binary search tree property. So this is the first case. Okay, second case. Deleting a node with one child case. If we are attempting to delete one node, that node contains one child means so we have some problem. So first in this example we will take the node as 54. Compare the value with the root node and locate the position of 54 where it is available. So now the compare with the 45 it is greater and compare with the 56 it is lesser, and now this is the 54 location, this yellow color. Now we are given the value as 54 as a deletion. Okay, for deleting value is 54. So now this 54 contains one child case. So the written node with the one child. So without the bypassing the connection of child, we cannot delete this parent because this 54 is a parent. Once I have deleted this parent means this child 55 is disconnected from the whole tree. So that violation is available here. So first we have to take care of that, then only we can delete this parent. So before deleting this parent, first we have to bypass the tree to the next level, and this 55 is connected with the 56, the connection will be bypassed. Then now this 54 removal will not affect the tree, rest of the tree. So now we can delete this 54. This is the case of second case. So deletion node have one child case. In the previous case, deletion node have zero children case. If it is zero means, for example, 55 means directly we can delete the 55. No issues of property violation for deleting of this 55. But next case, deleting a node with the one child case. In this one child case means before deleting this parent, first we have to bypass a child. So then only we can able to delete this parent. So this is the second case of binary search tree. So now we can go with the third case of deletion. So third case of deletion. Wait a minute. Yeah. So here deleting a node with the two children case. Okay, we are attempting to delete one node. That node contains the two children case. This is the third case. Okay, so here first we have to take a value and compare with the root and locate the value where your deleted value is available. So as per our example, the 56 is the deleted value. This will be available in the right of the 45. So here, this removal of 56, again it will violate the property. So if I have deleted the 56, this 54, 70, everything is disconnected from this root. So before 56, okay, okay, after the 56 deletion, I have to replace some value to this 56 position. So then only we can maintain the rest of the tree. So for that, so okay, after deleting this 56, we have the two option. One is left hand side child tree and other one is right hand side subtree. So here we have one option. So if the tree contain more than one value in the left hand side, we have to take a maximum value from the left hand side act as a root. And then if we have a more value in the right hand side, we have to take a minimum value from the root, minimum value from the right subtree, and that will be act as a root after the deletion of this 56. So this is a case one. So if the deleted node has the two children, after deletion of this 56, either we have to take a value, maximum value from the left subtree or minimum value from the right subtree is act as a parent after this 56 removal. So this is the third case. So if the deleted node has a two children case means after deletion of this parent node, so here we have to move some node for replace this position. Okay, so to complete the search tree. So here in left hand side more values available means we have to take a maximum value that should be a root. In right hand side means we have to take a minimum value that should be a root. So if you can take a maximum value, why we are taking maximum value from left hand side and minimum value from the right hand side means that values only will satisfy the binary search tree property. As all we know, we have the root node has some key. Lesser than the key is placed as the left, and the greater than the key is placed as the right. So if we are taking a minimum value from the FT means definitely we will have a rules violation of binary search tree property. To avoid that, always you have to take a maximum value from the left hand side, minimum value from the right hand side. So these are the three cases of deletion. Now we will discuss the algorithm for these three cases. First case is deletion will have zero children, and deletion will have the one children case, and deletion will have two children case. These are the three cases of deletion. So now we will check with the algorithm. Yeah. So this is the algorithm. We have three cases: deleting a leaf node with no children case, deleting a node with one children case, deleting a node with a two children case. So now, as usual, you have to take a function of deletion in the tree with the value, which value you want to delete. So take that okay function and compare with the root node. If tree equal to null, if the tree is empty means we can there is no meaning of deletion operation. So this is a precaution condition. Next, we have to compare with the root node value. Else, if the tree is not a null, it has some values. So compare the root value, whatever the input value we have taken for the deletion, take that value, compare with the tree data means root node data. So if it is lesser, go to the left subtree and apply the delete operation. Delete of tree left comma value. Else value is greater than the tree data means go to the right side tree. Okay, delete of tree right and perform the delete operation. So this is one case. Okay, if the deletion node should be a okay, if the deletion node has a two children case, first this is the deletion node has a two children case. If the tree left and tree right, both the node having both the children, tree left and tree right means we have to find the largest value from the tree left and then we have to place that value into one temporary node. Or if the tree has a right hand side right hand side more number of values means great find the smallest value and store into the temporary node. And then next this temporary node will be act as a tree data after the deletion of original parent. And then next, once you have moved the data, that occurrences will be there in either left hand side or right hand side. So that also we have to delete for the delete of tree left comma temp data or the delete of tree right comma temp data because the occurrence either should be in the left hand side or right hand side. After that, more value will be moved to the root. Then the occurrence also we have to delete. So next, else, if the delete node has a root node, there is the leaf node, there is no left and right case. If this okay, if the tree is set to the temporary node and there is no left and right means finally you can free the set the tree of null means that particular node will be deleted, leaf node will be deleted, the copy of value will be deleted. So else if the both the case, if the node has the tree left equal to null means set the tree left is on tree. Next, the parent will be as a left child should be a parent. Likewise, if there is no right means the right child should be a left means the right child should be a parent. This is a single child case, and this is a zero child case, and this is a two child case. So this is the algorithm of deletion operation. So totally in the binary search tree we have three operations: searching, insertion, and deletion. So on we have discussed. So what is the use of this binary search tree means to make a searching operation most efficiently. So through this binary searching concept, we can search elements efficiently. It will reduce the time, very less time. Within the less time, we can search. So this is the use of binary search tree. This will be mainly used in the big data and then the large volume of data. Wherever we can store the large volume of data, from that we need to find some data means it will be easily possible. The accessing is easily possible through this binary search tree. So next class we will check with the next tree, that is the AVL tree. So thank you all.